A machine smaller than a school bus just whispered back from a place where sunlight feels like a distant memory. It departed Earth carrying a golden record and a set of instruments meant to last 5 years. A simple flyby mission to glimpse the gas giants. That was nearly half a century ago. Today, this fragile emissary drifts through a void so absolute that our star's voice has faded into the background noise of the galaxy. It has pierced the heliopods, that turbulent shoreline where the breeze of our sun surrenders to the cosmic wind. And right at that border, the readings turn strange. Plasma density spiked. Magnetic field lines twisted into unfamiliar shapes. The radiation count climbed. The craft saw nothing visually.
The wall or signpost.
Yet the very physics of the space surrounding it transformed. This was humanity's initial brush with the interstellar medium. But here lies the haunting reality. After traveling longer than most people live, this probe is still chained to the sun's gravitational leaf. It escaped the solar wind's embrace, but it hasn't left the solar system. Between this fragile metal husk and true freedom lies an expanse so vast it defies human comprehension. A journey measured not in years, but in epochs. And somewhere in that endless night, a phantom structure awaits. A colossal sphere built from trillions of frozen relics. A deep freeze preserving the very material that birthed our planets. This is the domain of comets, the graveyard of creation myths. Call it the Oort cloud. The Odyssey began with ignition. A precise, trembling machine aimed at the darkness no one had ever dared to map up close. The trajectory arced past swirling storms and frozen moons, environments so alien they rewrote every textbook we had. Yet it was the fleeting rendezvous with Uranus, the sideways ice giant, that left behind the most perplexing riddles. Mysteries buried inside a lopsided magnetic field, and a tilt so severe the planet rolls around the sun like it's tipped over top. The data from that moment is decades old, but our curiosity is not. Now, armed with modern algorithms, we are peeling back layers to find truths the probe would never have articulated. Our entire comprehension of its magnetosphere may have been built upon a mirage, a snapshot taken during an exceedingly rare cosmic tantrum. The spacecraft arrived just as the sun unleashed a powerful gale of charged particles, a dense squall of solar wind that slammed into the planet and crushed its magnetic defenses to a mere sliver of their normal extent. Typically, the solar wind sculpts these planetary shields, creating vast bubbles that deflect dangerous radiation. However, during that specific week in 1986, pressure was so immense that Uranus's protective field shrank to roughly 20% of its expected volume. According to recent analysis published in Nature Astronomy, this configuration of pressure happens only about 4% of the time. Had the probe swung by merely a week earlier, it would have documented a sprawling magnetosphere comparable to those of Jupiter or Saturn. For decades, scientists accepted the portrait painted by that visit, a bizarrely empty kinetic field, though on plasma, yet crackling with intense radiation bounce. But the new interpretation flips the script. The solar wind didn't reveal a weak field. It temporarily swept the plasma away, creating a false vacuum. We mistook a fleeting storm for permanent weather. Beyond the last recognized planet, far past the frozen plains of Pluto, a titanic invisible border exists. Envision a spherical fortress of space occupied by countless ancient ice fragments. This swarm demarcates the final sphere of the sun's dominion. It appears in every diagram, as if it were concrete fact. We discuss it as a certainty. Yet there is a glaring, almost embarrassing contradiction. We have zero visual confirmation. Not a single pixel of light from this region has ever been captured by our lenses. We possess more detailed maps of neighboring star systems than we do of this local frontier. So why do astrophysicists treat its reality as gospel? And what if the models are fundamentally flawed? What secrets do the ancient paths of comets hold? And what do those icy arrivals tell us about the architecture of our own backyard? Whenever a comet swings close to the sun, its surface sublimates, boiling away into the gorgeous tail we admire. But here is the puzzle. If a comet made frequent visits, it would rapidly exhaust its ice supply and would become a dead rock. The fact that comets still blaze across our sky after billions of years tells us that they spend almost their entire existence somewhere else. They must hibernate in a cosmic freezer, a storage unit situated so far away that the sun is merely the brightest star in a sea of black. Another clue emerged from the trajectories. Unlike the flat, orderly orbits of the planets, many of these visitors arrive from steep angles, diving down from above the plane or soaring up from below. This random spherical distribution implies a source that is not a pancake-shaped disk, but a vast surrounding reservoir. By the mid-20th century, the stage was set for a sweeping hypothesis. Back in 1705, Edmund Halley recognized that the blazing apparition seen in 1531, 1607, and 1682 was actually the same body returning on a 75-year loop. This confirmed that some comets are permanent residents, not one-off visitors. But it begged a critical question. How could Halley's comet survive for millennia of repeated sunburns? The only logical answer was that it resides in deep freeze for most of its life. In 1932, Ernst Öpik, an Estonian astronomer, speculated about a distant reservoir of cometary bodies lingering at the fringe of the sun's influence. The idea simmered in obscurity until 1950, when Dutch astronomer Jan Oort revisited the problem with a fresh dataset. Oort studied long-period comets and identified a strange clustering pattern. The aphelion tended to pile up around 50,000 astronomical units away. For Oort, this was the smoking gun, pointing toward a colossal bubble of icy debris. His 1950 paper, he articulated the theory of a thick, spherical halo of dormant comets. The structure soon carried the name Oort cloud. To grasp the Oort cloud's isolation, we must first reacquaint ourselves with our solar system's known neighborhoods. From the asteroid belt to the Kuiper belt, these regions are flat, aligned, and relatively cozy on a galactic scale. Beyond the Kuiper cliff, the solar system thins into near emptiness, a sparse territory known as the scattered disk. Even at 1,000 AU, we are barely 1% of the distance to the Oort cloud's inner boundary. The Oort cloud begins here, a swarm of icy bodies stretching up to 50,000 AU, or roughly 0.8 light-years from the sun. Some projections suggest its outermost layer might stretch to 1.5 light-years, marking the true edge of our solar system. It's a region a quarter to half the distance to our nearest star, the most remote part of our solar system, the Oort cloud. Even Voyager 1, after 45 years of flight, is just a visitor at the gate. At 17 kilometers OS, it will take another 300 years to enter and 30,000 to escape. A silent abyss where ancient drifters have slumbered for eons. But now, one is awakening. In 2025, we detected a faint glimmer, an intruder from the edge of the system, aimed directly at the sun. Comet C 2025 R3. An ancient visitor from the Oort cloud, now on a collision course with our light, promising a spectacle from the edge of the cosmos. According to Orbital Mal, on April 20th, 2026, it will execute its perihelion passage, skimming past the sun at a safe but brightening distance of 0.51 AU, about 100 million kilometers. A week later, on April 27th, it makes its nearest approach to Earth, roughly 0.53 AU. That is a comfortable, safe distance, yet close enough to hang in the night sky like a faint ghost. The comet's path is extraordinary. It is tilted about 125 degrees relative to the planetary plane, meaning it travels backward, a retrograde orbit. Such steep, rebellious trajectories are a hallmark signature of objects that hail from the distant Oort reservoir. and its specific geometry between us and the sun could create an effect called forward scattering. If the nucleus sheds enough dust, the tail could reflect sunlight directly back at Earth, turning a dim smudge into a bright scar across the spring sky, perhaps even visible without binoculars. So when you scan the heavens in the spring of 26, understand that this glimmering visitor is more than a pretty sight. It is a frozen time capsule from creation's dawn, an icy courier dispatched from the most unexplored frontier we own. Now, let's examine the mechanics of the solar breeze more closely. When these charged particles slam into a planetary magnetic field, they exert a dynamic pressure that can squash, inflate, or reconfigure the magnetosphere. This interaction is fluid, changing with solar flares and the planet's orbital distance. On worlds with robust magnetic fields like Earth, Jupiter, and Saturn, the solar wind helps sculpt the protective barrier that shelters the surface from lethal cosmic rays. The magnetosphere is the planet's invisible armor, but it is not a perfect shield. Its size and strength are at the mercy of the solar wind's density and velocity. During the Voyager 2 flyby of Uranus in '86, conditions were at their most extreme. The dynamic pressure of the solar wind, a calculation combining intensity and speed squared, was near its maximum recorded value. In the typical circumstances, Uranus's magnetopause should stand about 22 to 25 planetary radii from the planet. But during that singular week, the boundary was crushed inward to a mere 17 radii. As the pressure spiked, the magnetosphere contracted violently. The intense solar gale swept the region clean, pushing that plasma out into space. This left behind an environment that was unnaturally empty, giving rise to the enigmatic, intense electron belts that confused researchers for so long. The new analysis suggests we observed a planet holding its breath, not its resting state. Astronomers now propose that the Oort cloud has a dual-layered architecture. The outer region is the classic spherical shell, extending from roughly 20,000 AU out to the farthest fringes at 50,000 AU, and possibly beyond. Beyond the known planets, objects are held by the sun's gravity with the faintest of silk threads. Over eons, the galaxy's tidal pull has scrambled their orbits into a uniform globe. This is the Oort cloud. But closer in, there's a denser inner core, often called the Hills cloud, a puffed-up version of the Kuiper belt. Why the dual nature? At 50,000 AU, passing stars' whisper is louder than the sun's shout. But closer in, the sun's gravity still keeps things aligned. But what are these phantom objects made of? Judging from the comets that have visited us, they are dirty mixes of ice and rock, frozen mud balls. Scientists believe the cloud's denizens consist of volatile ices like water, carbon dioxide, methane, and ammonia, all cemented together with dust and organic compounds. Estimates suggest there may be hundreds of billions, or even trillions, of these icy chunks. Most are modest in scale, though a fraction could be tens of miles across or larger. Some researchers have even speculated about the presence of full-fledged dwarf planets hiding in this shadowy census. Until recently, every known object arriving from this direction was icy and manifested as a comet upon approach. But in 2021, astronomers received a jolt. A fireball meteor that streaked over Alberta, Canada, was traced back to the outer solar system. To widespread surprise, this grapefruit-sized fragment was made of rock, not ice. It penetrated the atmosphere far deeper than a fragile icy piece would, revealing its dense, stony nature. Its orbital path was retrograde and highly inclined, exactly matching the signature of an Oort cloud native. How could a rocky asteroid get stuck in a freezer full of comets? The prevailing theory is that during the early chaos of planet formation, rocky bodies from the inner solar system were gravitationally ejected upward, mingling with the icy leftovers in the cloud. Indeed, recent research indicates that a small percentage, perhaps a few percent, of the Oort population may be rocky interlopers. The Oort cloud holds trillions of bodies. Why has it remained utterly invisible? The answer is twofold: sheer distance and profound darkness. A typical cloud object is only a few miles across, yet it sits trillions of miles away. It is akin to trying to spot a single grain of sand on a beach in Los Angeles while standing in New York. At such extremes, even a mountain-sized object reflects almost zero sunlight. Unlike stars, which generate their own light, or inner planets, which bask in a bright glow, Oort cloud bodies are inert and black. We can barely spot dwarf planets in the Kuiper Belt at 50 AU, and those are hundreds of miles wide. The combined light of the entire Oort cloud would be far too diffuse for any current instrument to distinguish from background noise. Given this vast, uncharted territory, it is no wonder that speculation runs wild. One notable hypothesis was a giant planet nicknamed Tyche, proposed in 1999. They noted minor quirks in the orbits of some long-period comets and suggested a hidden gas giant, perhaps several times the mass of Jupiter, might be lurking in the cloud. NASA's WISE infrared space telescope conducted an all-sky survey. WISE found no trace of a Jupiter-sized or larger world, effectively ruling out Tyche's existence. The allure of a Planet 9 still captures headlines. But what about rogue planets captured by our Sun? A 2023 study modeled the early cluster environment where the Sun was born. Simulations showed that stars can easily steal ejected planets from one another. Captured worlds usually end up on the distant fringes, right in the Oort cloud zone. The study estimated a 7% chance that our Sun snagged an ice giant from a passing neighbor. Intriguingly, the odds of one of our own native planets being kicked out that far are a minuscule 0.5%. The 7% chance means a secret sibling is unlikely, but not impossible. Still, no direct gravitational wobble or heat signature has been found. While the cloud itself hides, it communicates constantly through the icy messengers it sends our way. Astrophysicists agree that virtually all long-period comets originate from this region. This includes some of history's most stunning celestial displays. When a distant object receives a gravitational bump, it can begin a million-year freefall toward the Sun. By the time it reaches our neighborhood, it appears as a brand-new comet, never before recorded by human eyes. Such events are rare in a human lifespan, but on cosmic timescales, there is a steady trickle of these ancient arrivals. Most long-period comets are seen once and then retreat for so long that entire civilizations rise and fall before their return. Some trajectories are so stretched that the last time they swung by, Homo sapiens hadn't yet walked the Earth. Others are given a final gravitational shove by Jupiter, turning them into interstellar castaways doomed to wander the galaxy forever. An interesting subgroup is the Halley-type comets. They have intermediate periods of 20 to 200 years, but possess weird, tilted orbits. These bodies, including the famous Halley's Comet, likely began their lives in the Oort cloud, but were later hijacked by the gravity of the but over deep time. Two forces scrambled their orientations, passing stars and the galactic tide. Our Sun was born in a crowded nursery. During its first few 100 million years, other stars passed uncomfortably close. Even today, stars drift by. Schultz's star passed within 0.8 light years, roughly 70,000 years ago, grazing the outer Oort cloud. Such close encounters, combined with the gentle but persistent yank of the Milky Way's core, gently stirred the pot of distant orbits. Computer models by researchers like Alessandro Morbidelli show this process as incredibly effective at turning a disk into a sphere. The outer cloud, being so loosely bound, was the easiest to randomize. The inner Hills cloud, held tighter, retains a more disk-like memory of its origins. Thus, the sphere is a natural, inevitable outcome of galactic erosion. If our Sun has such a cloud, shouldn't other stars have them too? Astronomers strongly believe that or clouds are a standard feature of planetary system formation. The same mechanics, giant planets flinging out debris and stellar flybys shaping the edges, operate everywhere. We think most stars with planets are cocooned in their own invisible halos of comets. Indirect evidence supports this. When we see comets falling into other stars or debris disks with extended structures, it hints at distant reservoirs. Our solar system may have even exchanged material with sibling systems in our birth cluster. Direct detection of an exo-Oort cloud is, for now, beyond our technical reach for the same reasons we can't see our own. But there are clever workarounds. In 2018, astrophysicists proposed that a massive Oort cloud around a nearby star might leave a faint fingerprint on the cosmic microwave background. The idea is that a shell of cold dust and ice could ever so slightly absorb or scatter the background radiation, creating a ghostly shadow detectable by ultra-sensitive instruments like the Planck satellite. By combing through this data, we might find the silhouettes of other Oort clouds. After all, if this structure is a natural consequence of our own system's birth, the galaxy should be filled with these invisible cocoons. So, what is the takeaway regarding this grand, unseen edifice? It stands as one of astronomy's most compelling paradoxes, a structure of staggering scale that we cannot see, yet whose existence is nearly indisputable. It is a monument to the power of deductive reasoning. Just as the position of Neptune was calculated with a pen before it was found with a lens, Jan Oort peered into the patterns of icy wanderers and deduced the existence of a realm we may never visit in person. And today, that deduction has only grown stronger, bolstered by new evidence that confirms something is most certainly out there, lurking just beyond the reach of our telescopes. We have yet to design a probe that can survive the journey, nor build a camera sensitive enough to see a snowball in that void. But the next time a comet graces our evening sky, pause for a moment. Recognize the profound truth of its origin. A frozen halo, shrouded in the most perfect darkness imaginable, but nonetheless sheds brilliant light on where we came from, and how our small blue world fits into the sprawling architecture of the Milky Way. Please share the video and subscribe and like and comment on my video. Thanks.